Okay, so today we're going to be talking about Vsepr, which is a fancy way of saying what weird molecular shape do all of these covalent molecules take. We did Lewis dot structures, and that was a very two-dimensional representation, but very, very, very few molecules are two-dimensional. They have 3D shapes depending on how those electrons around each one of the atoms within the molecule want to spread out. I got a little bit of a bigger difference in my split screen today because I want to very strongly be using my molecules over here and be referencing our notes page back and forth so you guys can kind of get as much visuals as possible on this. So we're actually going to be splitting our notes handout that's on Vsepr theory and polarity into two different video lectures. I'd first just like to tackle the first page, our Vsepr shapes, and then work through our Lewis dot structures and Vsepr practice packet, get those committed down, and then we'll come back and do polarity as a separate lesson. I think that is the way it makes the most sense. So you'll need your note page out, and you'll need a couple of different colored pencils. It does not matter what colored pencils you use. Maybe don't use our classic red and blue, because then you may see the red and blue and think, oh, metals and non-metals. And these are just colored pencils that I'm going to use to kind of help us break up some of the two things that I look for to help me determine what Vsepr shape I am. So I'm using a light blue and a light green. So feel free to use those colors or different colors if you would like. Okay, but I'm excited to talk about Vsepr and how we determine what 3D shape our molecules are going to take. Okay. How and why do molecules make all of these weird and different 3D shapes? So I have a little bit of a smattering of molecules here, and you guys, they are not two-dimensional. They're taking up like all the weird shapes and spaces, right? Some of them may seem familiar to you, like we've totally got some water molecules in here. This actually, y'all, this is showing carbon dioxide. We know that carbon dioxide has two double bonds, right? This would be carbon and then 4 hydrogens around him, carbon tetrahydride here. That is definitely not two-dimensional. I do have shapes every now and then who do look completely flat, and that is a possibility, but especially when I get to bigger and bigger and bigger molecules that have more than, like, I don't know, 3 or 4 atoms bonded together, all of these individual shapes that I can create from different atoms in here will create these wild, really cool 3D structures when I look at especially macromolecules like within our cells. Okay, so Vsepr theory. Vsepr stands for valence shell electron pair repulsion. And let's have this conversation real quick. I am not a great English student, but I do think I can read like my letters in a row. This is V and then S and then E, P, R. Everybody, all your chemistry teachers will call this Vsepr, which in my brain, if you're going to call it Vsepr, that assumes that the E is coming before the S, and I'm like, that is not what we are seeing here. So I will always have the constant battle and struggle of saying Vsepr or Vsepr. I think I'm just going to, follow everybody else here and start saying Vsepr now. But yes, I do recognize that saying Vsepr does not match with the letters you see in that little word there. So anyway. So valence shell electron pair repulsion is a model that predicts the 3D shape of a molecule by assuming that electron pairs in the valence shell of an atom will arrange themselves around an atom to minimize repulsion. It's a fancy way of saying they're going to get away from each other because those like charges, those like negative charges will repel. So this results in a structure where the electron regions, which we will break up into bonding regions or lone pairs. So those electron regions are going to be as far apart as possible. So we've drawn the Lewis dot structure of water before, right? So this is an incorrect structure. We know that water is not a completely linear structure where the oxygen is in the middle and the hydrogens are perfectly, boom, straight on the outside. Okay, that's because he's got these, we drew some dots when we did our Lewis dot structure for water, right? And those dots make a world of a difference because if I were to look at my water molecule, he's that shape. So it's a fancy way of saying that, those bonds of the hydrogens are not going to be 180 degrees apart. There's something going on with these lone pair electrons on that oxygen atom that's going to make them We're going to talk a little bit more in a bit about what that means, but just basically here I'm looking at, I'm going to get some weird shapes just based on the fact that I've got maybe some lone pairs on these atoms. And also some bonds, because we know that bonds are made up of negative electrons who do not want to come into contact with each other either. So electrons repel each other just like magnets. Electrons do not want to be near each other. It's just like a magnet. We would know if we would put the north poles of two different magnets together, they're going to repel. Just like if we put two positively charged things together, they're going to repel. If I put the south poles of two magnets together, they will repel. But if I put opposite north and south magnets together, they're going to attract. Similarly, my positive and negatives will attract. That's called an electrostatic attraction, right? Okay. So anyway, the electrons will determine your shape. It is, once again, y'all, it is all about these electrons in my chemistry class. I love that. Yay, electrons. Good job for you. So valence electrons around an atom and between my atoms are all negative. So they will repel each other and will spread out as much as possible to minimize the repulsion. So I think we drew a Lewis structure for carbon bonded to 4 hydrogens, and it looked very much like, in fact, I can draw it. I can draw it right now. Let me get a piece of paper out. When we drew our Lewis dot structure for carbon bonded to 4 hydrogens, we did this. And that absolutely is a correct Lewis dot structure. Yep. But Lewis dot structures only show 2D. If I were to actually see what that structure looks like as a molecule, you guys, he is not flat like that with 90-degree bond angles. He looks like that. So that's why you're seeing this 109.5 angle between those bonding regions, is because those electrons in those 4 bonds can spread out a little bit more. It's going to make them have to take a 3D shape, but that is something that they will do to minimize that repulsion. All right, how to determine the 3D shape? You can draw a Lewis dot structure. Oh, we love that. And then we're going to count the number of bonding regions. We call this a BR. And the number of lone pairs, which we call an LP, on the central atom. Okay? And there's a little note here that says if I have a double or a triple bond, it still counts as only one bonding region. Okay? And then I determine the shape from a chart below. Okay, let's get out my page of notes that we've been cranking through today. I do want us to maybe up here, I know my NH3 on my slide does not match what anything you have up here, but we do have a water molecule. And I thought with my colors that we are designating as my bonding regions and my lone pair colors, we could kind of indicate this on here. So I'm using green for bonding regions. So we even wrote that here. So I can circle that and say that is a bonding region. So we will call that a BR. Wow, that is a light colored green. Maybe never again will I use this. That is okay. And then for my lone pairs, I'm going to be using blue. So LP is what we would see for lone pairs. So if I'm looking here on my water molecule, lone pairs are a pair of electrons, but only on the central atom is what I am interested in. I do not care what lone pairs are going on your outer atoms. Central atom, lone pairs. So I would see my lone pairs here for my oxygen, right? And then my bonding regions are going to be any connections that central atom is making to my outer atoms. And I do not care if it is a single, double, or triple bond. It will all count as one bonding region as it is going to an outer atom. Yes, so this would have 2 lone pairs and 2 bonding regions. So let's bounce on down here, and I've given you a big old chart. A big old chart of all the Vsepr shapes that you will need to know. There are 6 of them. There are way more than 6 possible Vsepr shapes if I have atoms who have expanded octets. But for my class, we only need to know 6, which is very exciting. But it makes it really easy if I'm just counting bonding regions and lone pairs. So you may want to, since we said our bonding regions were green, we can totally circle this green. And my lone pairs, we said, were blue. I can totally circle this blue. So that way when we go through each one of these examples, we will actually circle on our Lewis dot structure example what we are looking at and where those lone pairs and bonding regions are so we can count them. Cool. Okay, so we need to know the following 6 Vsepr shapes. Our 6 Vsepr shapes are, we have a linear shape, which is the first thing I have here. We have a trigonal planar shape, which is this guy right here. We have a bent shape. I call it bent, which is this guy right here. We have tetrahedral shape, which is this guy right here. Y'all were like, oh, there's my carbon tetrahydrite. We have trigonal pyramidal, which is this guy right here. And then finally, we have another bent shape. You're like, what? There are two different bent shapes. Yes, there are. And we'll get into what that means. Okay, let's see. Let's see our first shape. Our first Vsepr shape is a linear shape. And if you'll notice, I've given the bond angles of 180 degrees. That just means the outer atoms, those bonds, are literally a line as far apart as possible. Okay, so my example for that is actually going to be carbon dioxide. So here he is. As you can see, no matter which way I twist it, right? Those oxygens are totally, completely spread far apart. There's no kinking together or whatever like that. Now, the reason for this is that my carbon does not have any electron pairs up here. Nope, nothing. So all of the electrons are in these two double bonds, so they're going to get far away from each other as possible, which just happens to be in a 180-degree angle. But what is important for you, and we can even draw this, is I can go to my Lewis dot structure right here, and I can circle my bonding regions with my green. I do not care if it is a double bond. That counts as one bonding region. Yes. He's got, oh, that's where I get that two bonding regions, right? Okay, well, let's count lone pairs. Lone pairs only on the central atom. No dots for him, so he's totally got 0. So in the case where you have two bonding regions, meaning your central atom is bonded to two other things, and there ain't no dots around you, then that means he's going to create this linear shape. Very cool, very fun. Let's see what our next shape is. Trigonal planar. Okay, so an example for trigonal planar is this is actually BH3. Remember, boron is one of my exceptions to the octet rule. He only is fine with 6 valence electrons, and that is why you are only seeing 3 bonding regions, and all of them are single bonds. So I grab my bonding regions colored pencil, my green one, and I'm going to circle all 3 of those bonding regions and be like, yo, that's where I got the 3 from. Cool. And he does not have any dots on that central boron atom, so he's got 0 lone pairs. Cool. Now, I have an example of that guy. Like I said, he is an exception to my octet rule. So this is what it would look like if I had boron here and him connected to 3 different atoms. Okay, those different bonds, all 3 of them, are filled with negative stuff. So they are going to spread apart as far as possible to get away from each other. Noticing that he doesn't got no lone pairs on here, those 3 things are the only negative things the negative regions where I have to consider. Interestingly enough for this, the most satisfying shape for the bond or the electrons in the bonds to stay away from each other is to make it kind of flat to where those bonding regions can be 120 degrees apart. Okay, so that's actually, they call it trigonal planar because plane, he's flat. So if I spin him and look him on the side, he is completely two-dimensional, which is really cool. So this is my 2D 3D shape, which is, or my 2D 3D shape, my two-dimensional Vsepr shape is my trigonal planar one. Okay, let's see what the next shape is. Next shape is bent. So my example of bent, this is a nitrite ion. I've drawn the structure for my nitrite ion. I may zoom in a little bit more. So counting bonding regions, he is connected to 2 outer atoms. So he has 2 bonding regions. 1, 2. That is where I get this 2 from. Yes. And then he actually has a lone pair. It's our first lone pair example. How exciting for him. He's got a lone pair. I'm only circling the lone pairs on the central atom. Okay, so I'm going to go and circle this as a 1. If you'll notice, I kind of grouped this one and the previous one, the trigonal planar, together with this 3 business. Like, what am I talking about here? I like to think about some of these Vsepr shapes as being in families, okay? So these 2 guys are like brothers, okay? They are in a family that has, in some way or another, 3 negative regions here, whether those negative regions are all in bonds or in lone pairs. This central atom's got 3 things that he's kind of got to think about spreading as far apart away from each other as possible. Right? Now, this is kind of interesting because it can kind of explain some of our shapes here. Let me bring back this guy. What is it called? My trigonal planar shape here. Let's pretend that instead of one of these bonding regions being a bonding region, let's say, hey, no, you are not actually connected to anybody here, but you are a negative lone pair on that central atom. Then I would have something that maybe looks like this. Look at that. Do you see the difference here? You're like, but if I just got rid of that one thing, why is he not making a flat linear shape? Well, what you can't see is there's a big old negatively charged lone pair sticking up right there where the atom still feels and is going to cause some repulsion to force those bond angles still to be now you see it, a bent shape. And in fact, I can visualize, if I wanted to sneak my bent shaped guy in here, and if I actually showed the lone pair on this guy as that little like tan thing and say, to remind you that there is something there, it's just not a bond connected to an outer atom, you're like, okay, that makes sense why we're gonna have to make my bond lines kind of sneak into that weird shape. Okay, so this would be a bent shape here, and this is totally my nitrite. Okay, now you're like, cool, all I had to do was just remove a bond and he's a lone pair, and I still got 120 degrees. Slightly the bond angle does change. Whoa, let's see. So when I had three things, they were all 120 degrees apart. But here when I'm bent, now those bonds are even less than 120 degrees apart. That's weird. What this lets me know is that, you guys, that invisible electron pair is bigger. It's taking up more space than the electrons in a bonding region. So as a result of taking up more space, it makes the bond angles squeeze a little bit closer together than if it was just truly something that was connected to three outer atoms and having three bonding regions. Regardless, you guys do not need to know bond angles, but for us, I thought that would be very interesting to kind of explain that these lone pairs actually take up more space than my electrons in my bonding regions. I feel like I'm talking so much about this. I just really like Vsepr, so I'm glad to share this with you. But I do like to look at these families, because these families, I'm like, okay, everybody in this family totally has three negative things that he's going to orient around the atom, okay? So we've tackled half of our shapes, and if we're kind of looking at our list down here, these last three shapes, they're all in a family that has to accommodate four negative things around that central atom. Now, what those four negative things are is different depending on my shape. I could have all four of those things be bonds. I could have three things be bonds and one thing be a lone pair. Or I could even have two things be bonds and two of them being a lone pair. So let's get into these last three shapes. I'm super excited about it. Okay, tetrahedral. This is our first one of our four family. He's got four bonding regions. Our example that we did on him was CH4. I can see those four bonding regions. Very fun for my tetrahedral shape. He's got four bonding regions. He ain't got no lone pairs on him. No. So let's bring him out. Let's see what he looks like. Y'all, he does not look 2D like that. Y'all, he look like this. Wow. Yep. I can totally see now that these are not 90 degrees apart like my 2D picture shows. The picture, or the 3D shape, gives the atom the ability to get those bonds even further apart than my cute little 90 degree angles that I see on my Lewis dot structure. So that's what gets to the 3D shape here on my tetrahedral shape. And the bond angles are 109.5 from each other. Okay, let's see. Now let's say we substitute out one of these bonds, take it off, and now say, okay, no, you are only bonded to three things. That remaining section that would have been a bond if there were four things around the central atom would now be a lone pair. And I want to see how that affects the shape. Now we get to a trigonal pyramidal shape. So if I remove one of these bonds and I now give it a lone pair, I get this guy. Y'all are like, cool, we've seen another trigonal thing before. He was flat. Well, not in this case. If I look to him to the side, he's kind of got like a little like his lone pair at the top is kind of like a hat that he's sticking up on the top. You would call this a trigonal pyramidal shape. He is not flat. Here's some give to him right here. Okay, well, why? Why was this trigonal planar shape flat and this one was not? That's because this one had a lone pair, right? We have three bonding regions and one lone pair. If you go back to my planar shape, he had three bonding regions and no lone pairs. This guy's got an extra negatively charged thing on the central atom for him to kind of have to move everybody around, okay? So yes, I have two trigonal shapes, but they are different. And the way they are different is because of the presence of this lone pair. And in fact, if I wanted to visualize what that lone pair looks like, I can bring my guy out here that shows the lone pair as like, you know, this tan thing. And you're like, oh, okay, yeah, that makes a little bit more sense on how if I took my normal tetrahedral guy and said, okay, remove one of your bonds. Well, if I removed a bond, I still got a lone pair on there. So I am still in this kind of situation where I've got to accommodate 4 things on my central atom. Now, here's something that's interesting that I actually really, really, really love to look at. My bond angle changes slightly. We said when I was connected to truly 4 things and made 4 bonds, all those bonds be 109.5 degrees apart. Here, they're 107 degrees apart. That lone pair is making my bonds have to squeeze closer together. Remember we mentioned before on the previous examples with that first bent shape we talked about, that lone pair is actually taking up more space than my bonds do. So that means my bonds have to accommodate for that and squeeze in together a little bit tighter, which explains that decrease in the bond angle that I see here. Okay, so that's super cool, super fun. We love that so much. Now, what if I wanted to remove another bond? Well, then I would now have 2 lone pairs. Oh wait, y'all, I haven't even done my circles. I got too excited. I got my circles. Okay. So on my NH3 molecule, we can totally see my 3 bonding regions, right? So that's my 3 right there, and we can see that lone pair. But if I add that 3 plus 1 together, oh, he's still got 4 things to have to rearrange from his atom, except just unlike the last time, one of them now is a lone pair. So if I zip on down here, what if we got 2 that are in bonds and 2 that have 2 that if are in bonds and 2 that have lone pairs? What happens? What happens? What happens? We've got another bent shape. You've seen this guy before. This is our water molecule. You guys, how fun. Yeah, that's his Lewis dot structure shape. You're like, cool, I love this. 2 bonding regions, right? And 2 lone pairs. And y'all are like, but we look so linear. Why are we not linear? Well, I mean, we are clearly not linear with my water molecule, but why? Well, he's got 4 things to have to move stuff around. And if he's got 4 things, I do not care what you think in your brain. It is not going to be this perfect 90-degree thing apart for each one of my negative stuff to where those bonds are 180. No, what's going to end up happening is that, yeah, those negative electron pairs are going to kind of tetrahedrally move themselves around the water molecule, or the oxygen within the water molecule. So if I were to visualize these 2 lone pairs and the effect that that shape would have, I'm going to scooch my paper out of the way because I feel like we cannot see. Okay, look. Those are the lone pairs. And y'all can see now that it does look tetrahedral in shape, except my lone pairs are not going to be visibly connected to anything. But if I bring my true tetrahedral shape back out here, it's like you can see a lot of the similarities in there, right? So that's why we have this bent shape. If I make the lone pairs invisible like they kind of are, that's where we get that, which is really exciting. And here's something also really, really cool is I've added now an extra lone pair. Lone pairs are bigger and take up more space, which is why we see the bond angle get even smaller than it was in trigonal pyramidal, which was smaller than it was when I was tetrahedral. Very exciting, very fun. There are a couple of tips in here. You're like, oh my gosh, how am I going to have to memorize this? Well, tetra means 4. So if I totally am bonded to 4 things with no lone pairs on the central atom, tetrahedral is your shape. Linear, I feel like, is also pretty straightforward. Got 2 things, no lone pairs, you're going to be linear. My trigonals, I have 2 of them, okay? I've got trigonal planar and I've got trigonal pyramidal. The way I think about this is my trigonal planar was my flat 2-dimensional one, right? Whereas my trigonal pyramidal guy, if I wanted to pick the one visualizing the lone pair, right? I like to think about my trigonal pyramidal guy being like a little pyramid, like he's got a little pointy lone pair party hat. He's a little bit more fun, which means he is not plain like my trigonal planar. So trigonal planar is plain and boring, no lone pairs on him. Trigonal pyramidal has got a real fun pyramid party hat on his head. Y'all are laughing and being like, this is ridiculous. What is wrong with her? But you will remember which is exciting. And then my bent shapes, they will always be the shapes where I'm bonded to two things, but I have lone pairs on the central atom in some way or another. So this bent shape had one lone pair, this bent shape had two lone pairs. You are not responsible for knowing the difference between the two bent shapes, but I did put them on here because obviously they are different in some way, and then it relates to what family member or what family grouping they are in. Okay, very exciting. I did want to kind of talk about, I don't want to talk about this. So we mentioned, I brought these up on the screen a bunch, even though we can't see the lone pairs, you guys, them being there do affect the shape in some way, right? So this was my group of threes family, right? My trigonal planar and my bent shape. And the difference that causes that shape and the bond angle difference is that lone pair. Ooh, we subbed out, if you want to think about it, a bond for a lone pair. And then in my group of fours, my kind of tetrahedral family, here I would see the true tetrahedral bonded to four things. And then if I'm bonded to only three things, you would have a lone pair now. Means you're trigonal pyramidal. And then if you're only two things, you will have two lone pairs. And that's where you get that water molecule, that bent shape. So lone pairs make a big world of difference, even though we cannot see them. I do want to talk about these because they're kind of fun. So you do not need to know these next two shape categories. They are for my expanded octets, but I did have some examples of some of these shapes that I thought we could totally show together. And y'all would be like, wow, that's so weird that this is allowed to happen. Yes. Okay. Trigonal bipyramidal. So this is an example where I have 5 bonding regions and 0 lone pairs on the central atom. So if I can get out, oh my gosh, my guinea pigs just started squeaking because they hear the plastic bag of my Vsepr shapes and they think it's food. It is not food. That is wild. Okay. This has, yes. Okay. So here is a trigonal bipyramidal shape. As you can see, he's got 5 guys bonded to him, which is wild, right? So you're going to get some weird bonding angles like, y'all, some of these be 90 degrees. Yeah? Look at that. But then also in some cases, you're going to see like 120 here. So you're going to get a few different types of bond angles. Now, here's the cool thing. I could call this like a trigonal bipyramidal family. And what you see here is the other options of what shapes you can create if I just subbed some of these bonds out and replaced them with lone pairs. You get some weird stuff going on here. And in fact, if you have 3 lone pairs and only 2 things, you do create a linear shape here, which is really fun and really cool. You do not need to know these. I just thought I would show you because they're kind of fun. Octahedral. Let's see octahedral. I got to go back to my bag, which means my guinea pigs are going to start to squeak. Hopefully not. Oh, good. They've learned something. We are all learning something today. Okay. Look at that. He's bonded to 6 things. Totally an expanded octet. If I'm bonded to 6 things, I got 12 valence electrons. But every single bond is 90 degrees here, which is really cool. And just like last time, I got even more options of what I can get, what shapes I can get if I take out those bonds and create lone pairs, okay? Once again, I got a linear shape here if I only have 2 things, and those 4 other lone pairs will orient themselves around the central atom in a way that will create a linear shape. But this one is actually really fun. This square planar, I do have an example shown of that. Square planar, if I have 2 lone pairs and 4 bonding regions, it's a planar shape. He's actually 2-dimensional because the bonding regions will orient themselves on the opposite sides. So he's the flat option. Anyway, I thought I would just show these because I think they're kind of fun. These exceptions to the octet rule. Like, how fun and how satisfying. But you only need to know your 6 Vsepr shapes, right? So my 6 Vsepr shapes as a recap, let's see if I can zoom out a little bit, is our first shape we had was a linear shape, right? Where I have 0 lone pairs on the central atom and 2 bonding regions, meaning bonded to 2 outer atoms. My next Vsepr shape was my trigonal planar, and my trigonal planar has no lone pairs on the central atom, and he's got 3 bonding regions. He's 2-dimensional, he is plane. If I took one of those bonds out and subbed it with a lone pair, I would get a bent shape, right? Where I have a lone pair that you cannot see up here, but is causing this bent shape. So 1 lone pair and 2 bonding regions. We get that bent shape. So I'm getting my families. This is my family of 2 total things. This is my family of 3 total things to have to accommodate for. Let's get to my family of 4 things, starting off strong with tetrahedral. Tetrahedral, right? In fact, I'm going to go back to my slide. That is recapping all these things that I'm showing because I'm actually putting them in the right order. Yeah, look at this, look at this, look at this. Here's my tetrahedral. Look at that. Yes? If I took off one of those bonds and said you are now a lone pair, that is fine. It's going to make this weird, it's hard to see. It looks 2D, but trust me, he is not. He's got that trigonal pyramidal shape where his lone pair is making a little fun top hat, pyramid shaped top hat. And then finally, if I took out 2 bonds and I have 2 lone pairs, this is where you get that bent water molecule shape. So these are my 6 Vsepr shapes that you need. Not a big deal on assigning shapes. It is all about how many bonding regions and how many lone pairs you have. Okay, so the next thing we're going to do is we're going to pop out our Vsepr and Lewis.Structure practice packet, and there's even sections on there where we can now go back to our structures that we've drawn, figure out what Vsepr shape they are.